Howdy. In today's video, we're going to talk about flowing gases and gas viscosity as the first of a set of transport properties. In the video overall, we'll talk about viscosity as well as thermal diffusion and then diffusion of actual molecules or matter through the gas. Okay. All of these cases are things that you're probably familiar with from some of your engineering courses. Where the emphasis, I suspect, is on what here we will refer to as a phenomenological point of view on things, which essentially just says we can look up a viscosity coefficient, say, for a given gas, and know the equation we need to work with that and figure out how it's going to behave. What we're going to talk about is the kind of molecular scale underpinnings of those coefficients and look at least a little bit at the origins of them in terms of some of the kinetic theory ideas that we've been talking about for a while now. So the first difference in this and what we've been doing is now we're talking about a flowing gas. So a gas that's actually moving and collectively through a pipe, say. Right, so it's flowing in response to something like a pressure gradient that says the gas is going to go from high pressure to low pressure. Because of that, the molecules in the gas have excess kinetic energy or more kinetic energy in the flow direction than they would just from being at the temperature that the gas is at. Right, so normally we think about, or we've been thinking about gas that's just in a container. The gas as a whole is not going anywhere, right? And that leads us to the equations that say the average kinetic energy of the molecules then, for example, is 3/2 RT, right? But 3/2 RT. In the case of the flowing gas, there's going to be more kinetic energy because the whole gas as a unit is moving downstream through the pipe. Viscosity is a measurement of the resistance of the gas to flowing, okay? The higher the viscosity or the higher the viscosity coefficient is, the more resistant the gas is to flowing through the pipe. The origin of the viscosity is primarily the diffusion of molecules perpendicular to the flow direction. And so we'll look a little bit at how that happens. So the molecules are moving through the pipe like this, and as the molecules actually diffuse along this axis, that's going to be the origin of the forces that give rise to viscosity. So again, the viscosity is essentially a resistance to flow in the gas. That's the first comment there. And if I picture a gas, this little schematic over here on the side has a gas that's flowing from left to right on our screen, okay? And in the gas, we've got vectors here that represent the velocity of the gas, the flow velocity of the gas at different points in the pipe. What those suggest is that the gas along the walls is moving the slowest because it's essentially encountering friction. We could say the gas in the center of the pipe is moving faster. All right, and there's a gradient going between those two limits. This circumstance is what's known as laminar flow. Okay, this is a different set of circumstances than, for example, the molecular flow situation that I asked you a question about in the exam that you took recently. So as this gas is flowing, we can picture this as being made up of a stack of layers stacked up in this direction through the pipe. Okay, those layers are going to slide relative to one another because they're moving at different speeds, and there's a friction associated with that, and that's the origins of the viscosity. There is an equation here for the so-called phenomenological equation. Eta is the viscosity coefficient. The u direction in this case, this is a little bit confusing. Here I use the du because that's the way this is described in the derivation in your textbook and in the figure that will come up next from the book. This figure over here actually uses u for the speed, which is a little bit confusing. The u direction here is actually this direction, the direction perpendicular to the flow direction in there. Okay, so we're going to take at least a quick look at the molecular origins of how this viscosity comes about. What I'm going to do is I'm just going to set up the basic argument here. In the slides that I posted for this, I did include a few slides after this that would lay out more of a derivation of the equation for the viscosity coefficient. I'm not going to go through those here because it's a little bit of a grind to get through them. It's the sort of thing I would much rather do with people in the room where I could see your faces as you're reacting to what's going on, and also where you could catch me if I happen to do something foolish while I'm trying to talk my way through the derivation. So if you're the sort of person who's curious about things like that, I did put the slides in, and there's also a more thorough derivation in the textbook that you could read through as well. So here's our flowing gas, a slightly different version of the figure. This one is from your textbook. The flow direction is here. Okay, so this f of x over there, that's just the overall flow moving in the x direction. What we've got here is we're going to imagine a couple of plates in the gas. Up here on the top, I've got the upper blue plate, and down here I've got the lower blue plate. And assume the lower one is closer to the wall of the pipe that I'm looking in. All right. The top plate is flowing through the gas at some speed u, and that's indicated by the vector over here with the u on it. Okay. The lower plate is fixed down here. All right. And that says that as these are moving, I'm going to have this relative movement, and there's going to be a gradient going across there. Okay, so the speed of the gas molecules in the flow is going to be decreasing as I drop down through the various layers. If I take this thing and picture it as not just those two plates, but plates with a lot of layers of gas in between them, my gas gets slower and slower flowing as I go down. This slide is also reminding me that in the last slide I misspoke when I talked about what U is. U is still, in fact, that flow, that speed of the gas as it flows through the pipe. And so ignore what I said in the previous slide, I'm afraid. As these are flowing, molecules are also free to diffuse in the direction that's perpendicular to the flow direction, right? So in our figure, that's the y direction up here, right? So the gas is flowing, say, this way, but molecules can also diffuse in this vertical direction. And what that's going to do is it's going to transfer momentum because the molecules coming from the fast-moving layer up here have more momentum in the x direction than the molecules coming up from below. So what's going to happen here is that molecules that are diffusing downward are going to be bringing x direction momentum with them. Molecules that are diffusing upward are going to be coming in with less x direction momentum than the molecules that they're replacing. All right. So there's a net transfer of momentum between the various layers in my gas. That's the molecular origin of where the viscosity comes from. Okay. At this point, I think what we're going to do in the diagram in the middle there is part of the argument to be made. So it's got lambdas in there for mean free paths. It's got arguments about how the diffusion would take place and what the net flow of momentum would be going in the upward and downward directions. And again, if you want to, you can work through that. I'm going to cut to the result here, which is this. Eta over here is the viscosity coefficient. All right, and if we look on the right-hand side, we see we've got a number of things that you'll recognize as being some of the parameters we've been talking about as we work through the other gas relationships we've had. So on the bottom here, I've got sigma. That is still the collision cross-section for the molecule, right? So it's related to the size of the molecule. And then to the right of that, I've got this mkt over pi all to the 1/2 power. That's a clump of terms that we've been seeing quite a bit. Collections of those in various arrangements have been in the equations for all the different speeds and things of that sort. So it's not too shocking they occur here again. They actually get into here by starting from some of the equations for, say, the speed of the gas molecules is part of the derivation, because there was a mean free path argument that would have been made if we had gone through that, okay? Some of the dependencies this bears out are a little bit counterintuitive. One of the first ones is that the viscosity does not have a pressure in it. So if you look at that equation on the right-hand side, there's no P anywhere, right? There's not even an N, so there's not an N or a V, so I can't relate anything in there to the pressure. The viscosity coefficient is independent of the pressure. That's perhaps a little bit strange. The viscosity increases as temperature goes up. That, at least to me, is also kind of strange, partly because your thinking or my thinking is influenced by liquids, where if I have a sort of a syrupy liquid and I want to get it to be able to pour or flow more readily, one of the first things I'd say is I'm going to heat it up. Right? If I'm trying to pour molasses in the kitchen and it's just too thick, then I know if I warm it up, it will pour more readily. Gases will do the opposite of that, is what this equation suggests. There's a comment there that says, other things being equal, large molecules will have smaller viscosities. And that's a little bit more complicated, because it's true, I've got the sigma down here, and if the molecule is physically larger, sigma gets bigger, right? I've also, however, got an M up there, and as the molecule gets physically larger, it's presumably likely to be getting heavier. right? Still, the shrinking part with increasing size generally wins out because the mass on the top is inside the square root and the sigma is down there by itself on the bottom. And that means as my molecule grows, that viscosity coefficient is most likely going to get smaller. I might be able to come up with some arrangement where I had somehow a physically larger but light molecule. I can't think of one right now, but in general it should be that as the molecules get larger, I should be having the viscosity go down. That again is the opposite of what would happen for liquids, where we sort of think of long tangly molecules as becoming more entrained with one another, and that increases viscosity. Right? If you're working with oil, the more long chain hydrocarbons you have in it, the higher the viscosity should get, because those just slide across each other less readily than the smaller molecules. The way this equation was derived, it's strictly speaking, it's correct for a dilute gas of hard sphere molecules, okay? It does still give us some general insight into the molecular origins of the properties associated with viscosity, but it's not, the values we get out of it are not always the best. What it's useful for is saying, if I want to try and compare what should the viscosities be for two different gases, say, I can use the ideas in this equation to think about how those should differ. And as long as the conditions are similar for the two, then most likely I'm going to come out in the correct direction by thinking about it this way. I'm going to do a quick calculation here, partly to point out some strangeness in units associated with viscosity. So the viscosity coefficient for nitrogen is given here, 176. That unit is micropoise. And the poise is a somewhat peculiar unit because it's based on CGS units and not on SI units. And so that gives us a somewhat unusual conversion factor for that one. From that value, we're going to estimate the collision cross-section for neon atoms, right? That viscosity coefficient is something that could easily be measured experimentally. And if we needed to get a value for that cross-section, this is one route we might take to get there. So on the slide, I've taken the equation for the viscosity coefficient and I've rearranged it to solve for sigma, which is this one, right? And so that tells me what I want to do. In order to do this, I have to do some work on that micropoise entity there, okay? It turns out that one micropoise, I'm going to get that as quickly as I can into SI units. One micropoise is actually 10 to the minus 7 Pascal seconds, or that would be what? That would be Newtons per meter squared seconds, and right? And so that's my my SI units for this thing. The 10 to the minus 7 there looks wrong, but it's actually the right thing to convert this. And again, that's because the poise unit has its origins in CGS units, which it's been a long time since anyone consistently used those. But the actual SI units for viscosity are very rarely seen. And so that's just sort of the way this is most likely to come up. Armed with that, I can say that my 176 micropoise should translate to being what? Well, I'll just write it as 176 times 10 to the minus 7 in Newtons per meter squared seconds, okay? Armed with that, I can now set up my calculation, and I think I can fit it all on here. So let's say sigma is equal to 2/3. I've got down here on the bottom, I need my coefficient, which is 176 times 10 to the minus 7. Let me put all my units in here because I do want to make sure I get them right in the end. Right, the seconds are not there. The seconds are up here, I believe. Then I've got a square root term, which is, oh, the mass. I did not work out the mass for the neon molecule. I hope you'll forgive me if I just write in here that it is apparently 4.65 times 10 to the minus 26th kilograms. And I hope that's correct. I just have that number in the notes sitting next to me. I've got a K, which is 1.38 times 10 to the minus 23. I promise I wrote there, 10 to the minus 23. That's joules per Kelvin. My temperature My pen is doing funny things here. My temperature is 293 Kelvin. On the bottom, I've just got a pi, I guess. So I do that and pi. And all of that is in the square root. I did not draw that way. And if I figure all that stuff out, my notes tell me that I believe I get 2.93 times 10 to the minus 19. That's in square meters. And that would give me 0.293, I guess, in nanometers squared, just because that's the kind of units we've been using most often for the cross sections, okay? And that's about the right order of magnitude, right? Tenths of square nanometers are what we've seen for these. This is it's nitrogen. Oh, it is nitrogen. Sorry, I thought I was doing neon for some reason. So when I said that was the mass, I was thinking that sounded like the mass of nitrogen, and for some reason I had it in my head that I was doing neon. Oh, because it says neon atoms here and nitrogen there. That's why I'm very confused. I actually calculated it for nitrogen, it looks like, and I did that. Yeah, that's the calculation for nitrogen and not for neon. The statement of the problem is what had me kind of flinching at that mass, because I was thinking I recognized that. Okay, so that one is not for nitrogen atom, for neon atoms, that is for N2. Okay, well, we'll see. Maybe I'll decide to do that one again. Next up in this sort of quick tour of the transport properties is thermal diffusion, which is just going to be the conduction of heat through a gas due to a temperature gradient. I am confident that you all in your engineering courses do various things involving the flow of heat through different systems, and so you're likely accustomed to such things. The phenomenological equation, again, just says that H is the flow of heat there, kappa is a thermal conductivity, and I can relate those two things by a temperature gradient, right? dt, dy here, where, so the viscosity is due to a gradient in flow speed, or in the momentum in the gas. This is due to a gradient in the temperature. And if we do the derivation is actually somewhat similar to what we talked about. It's actually a bit more complicated for this one. The result is as follows. Kappa, that diffusion coefficient, has the form listed there. The most complicated part of that is the F term in there. F is the active degrees of freedom, which generally speaking means translation and rotation for things at kind of ordinary temperatures. Right? Remember, for most molecules, vibrational states don't get significantly populated unless the temperature is extremely high, which is why it says for translation and rotation there, okay? So that F is divided by 3. There's another KT over pi m, which comes from the molecular speed equations. That's in the square root. Then there's another Boltzmann's constant out here, and there's our cross section again. That F term, degrees of freedom, if I have a single atom, that's going to be 3. Right? If I have a linear molecule, that's going to be 5, because a linear molecule, remember, gets 2 rotations, the one that goes like that and the one that goes end over end that way. It does not get the one that would be along the axis of the molecule, right? So there's just 2 rotations. That gets me to 5 degrees of freedom. If it's a nonlinear molecule, then I would get 6, because then I would have 3 rotational axes for the 3-dimensional molecule if it's not linear, okay? The dependencies there are, again, it's independent of pressure, right? This one is proportional to the square root of temperature, right? T is on the top, so as temperature goes up, my thermal diffusion coefficient should increase. I have the cross-section is on the bottom, which again says as the molecules get larger, my thermal diffusion coefficient should be getting smaller, because both M, the mass, and sigma, the cross-section, are both on the bottom this time, right? And so that means all the factors that lead to having a larger molecule are leading to having a smaller value of kappa. Oh, in the slides from last year, it looks like I had a clicker question at this point, and so we'll do a quick reading of the question, and then you can take a second and work on answering it if you'd like. For the results for Kappa, how would the thermal conductivities for helium and nitrogen compare to one another? Okay, and I included on the slide the Kappa equation over there to the right. And so you can pause if you want to have a moment to think about it. This is relatively straightforward. The things that are going to be different, the mass of nitrogen is certainly larger than the mass of neon. The cross-section for nitrogen should also be much larger than for helium, rather, right? Helium is a much smaller molecule, if you want to call it that, just a single helium atom. And so both M and sigma should be larger for the nitrogen case. They're both on the bottom of that expression, and that means that the thermal conductivity for the nitrogen should be the small one. So I would have to be choosing A for that one, it looks like, based on that. Okay, and that's not a very difficult question, so my guess is that most of you agree with that. Last on this list of properties for this go-round is diffusion, actual diffusion of matter through the gas, okay? The gradient in this case is going to be a density gradient, right? If I have gas where it's open container, but the gas is for some reason more dense on one side than on the other, then we know what's going to happen, right? The gas is going to spread out so that the density or the pressure, we could say, equalizes throughout that container, right? That has to happen. This is more complicated mathematically than either of the other two. Okay, so even in the textbook, the arguments made for this one are what often are referred to as hand-waving arguments, meaning it's just kind of a broad discussion of what's happening. The relatively simpler case, I won't say simple case, simplest case, a little bit simpler, is to think about so-called self-diffusion. Okay, to conjure that up, you need a somewhat unusual or artificial situation, one in which, say, we have a mixture of isotopes where I can tell them apart. So suppose I had a container and I introduced into it from two different sources, one on each end of the box. Say I mixed in, I don't know, I could say like H2 and D2, but then the masses are different enough that it would be perhaps a little bit bad to say that. Gosh, let me go with, I'll go with bromine, Br2, because I put a question in your exam that involved isotopic exchange in bromine molecules, right? Bromine atoms are heavy, so if I have Br2 of two different isotopes, the masses of the molecules are very close to the same. So we'll just assume they're the same, right? And then I could watch as the two things move through one another, because I start off with one isotope over here, one isotope over there. There's going to be a gradient, right? Eventually, if I give it time to let it disperse itself, they're going to equalize, right? So I'm going to have a net movement of each one across the box and into the other, okay? In this picture, what's done to represent isotopes is just that if you look closely, a number of the molecules, like that one there, have these little asterisks on them. They should show up as being a little bit darker, right? So if those were, say, radioactive molecules, we could watch them as they moved from place to place in the container. And if we started off with a bunch of them on one side, we could see how long it takes them to wander through the volume. The results for this are on this slide. And again, this is a complicated thing to derive, but we get that the diffusion, the diffusivity there, there's that D11. The 1,1 means for the same molecule diffusing into itself. So essentially it means that both molecules are otherwise the same as one another, that they're just differing in this, this density gradient for whatever reason. The isotope part, that's just because that's the only way you could tell what's happening, really. That's the only way you could follow the molecules, right? It's this gradient in density, right, which is why it's got the d n over v over dy, right? N over v is just the number density. That diffusion coefficient, the D11, can be shown to be given by the equation on the bottom, okay, which has in it again a KT, it's got M, it's got sigma, the cross-section, and this time it does have a pressure in it. It's got the P down there in the bottom. Okay, so that gives us some idea of how these things would vary. If we tried to compare different molecules, we could look at those parameters that are in there and see how they would stack up against one another. The more complicated situation is the diffusion of two different gases, where I start with one gas on one end of a container, another different gas on the other end of the container. And again, we know they're going to mix, right? It's going to take some time, but the gases are going to get themselves diffused together. And so that one, the ones and twos here represent, say, the two different gases, right? So the D12, that would be the so-called inter-diffusion coefficient for the two gases mixing with one another, all right? And that one is related to the mole fractions of the two gases. That's what X1 and X2 there are, and the self-diffusion coefficients, the D11 and D22. So that's the coefficients for diffusing either gas 1 or gas 2 through itself. And the interdiffusion coefficient is just this linear combination weighted by the mole fractions of the two self-diffusion coefficients, okay? In general, in being in chemical engineering, you're likely to encounter dealing with all of these things in the sort of phenomenological sense. That's a tough word to say sometimes, where you know that you can look up coefficients for these and figure out things like the time it will take for your gases to mix, say, in this instance, right? What have you. The equations we just looked through here are just ways to get at least a little bit of insight into the molecular underpinnings of those coefficients, which is in some circumstances can be useful if you're trying to choose an alternative gas for something and you really want to tinker with a particular property. It can help a little bit to just have some idea of like what sorts of things are likely to be good candidates from doing this, okay? And I believe that concludes what we've got to say about the transport properties, okay?